So I want to start off this panel by thanking the corporate sponsors for getting behind the annual symposium. Having been out on the corporate side of things, I know how difficult those sponsorship dollars are and how you have to budget them throughout the year, and you always get more requests than you can handle. So we really appreciate the fact that so many companies stepped up to sponsor this year's symposium. Now, you heard the first two keynote speeches from Charlie Bolden and Dr. Holdren that were kind of at the 100,000 foot level of space policy and how this administration would like NASA to go forward. Now, and it follows a theme, of course, of more than you can imagine. So now we're going to dive in a little bit to a little lower level of how are we at NASA through our mission directorates actually going to implement those policies. Our only instructions from the program committee was to discuss the programs that are coming up and to, quote, highlight activities that are not quite as well known, things that you haven't heard about quite as much. So it's going to be, our goal is to lift your spirits and to reassure you that despite all the uncertainty, despite the budget zaniness that's going on, that we face at the moment, that NASA is doing great things and that we bring value to the American public every day. Now, Charlie talked about he's excited about coming to work. I am also. When I hear so many of my fellow colleagues talk about how distressed they are and they can't come to work, they don't know where we're going, they don't know this, they don't know that, we still seem to be spending $18 billion a year, so we must be doing something. So get over it, come to work, and focus on the future. For those of you who are tweeting our session, I'm afraid I have some disappointing news to tell you today, and that is I had a 5-second delay sensor inserted into my brain the other day. It's designed to keep me from saying any career-limiting statements that could come back to embarrass the administrator during a congressional hearing. So if you're going to tweet anything and try to get a gotcha on anybody, it'll have to be with my colleagues. We're going to start with aeronautics. We're going to start closer to Earth, work our way out into the universe, and then come back at the end with Woodrow Whitlow to talk about the mission support requirements that we have to support all these things. We've got about almost 2 hours to discuss. I don't think we'll use all of that. Our presentations will be succinct and highlight what is coming up, and then we want to make sure we leave plenty of time for questions. So we're going to start with Tom Irvine from the Aeronautics Mission Directorate. Tom is the Deputy Associate Administrator. He has been at NASA since 1982 and has had experience in not only aeronautics but also pulled a stint for a while on the space station program. He's a specialist in research engineering, project management, and he originally got into all this because he was good at design analysis of jet engines. So Tom, please come up.
Thanks, Alan, and I want to thank Harley for showing that James Webb Space Telescope clip, because science has absolutely the coolest videos. And maybe 50 years ago, aeronautics videos were really cool, but somehow they just don't stack up compared to science. So I have about a 15-minute presentation, and if it works as planned, it's because of the magic of Jay and not me. And I'm just hoping it works as planned. I think the title of this session is NASA More Than You Imagine, but since this is aeronautics, it may be more than you bargained for. And this being the Astronautical Society, I really appreciate your patience with our story on aeronautics. So Alan had sent me an email, or sent all of us an email on Monday that said, tell the audience something that they may not know. This being an Astronautical Society, I figured I'm good to go. This is aeronautics, so I'll go first, and hopefully we'll tell you some things that you don't know. So the way I want to do this is sort of stand a usual presentation on end, where you usually start by telling people like why you do what you do, and then you kind of work through like what you do, and eventually, in typical NASA fashion, we always say, but really our most valuable asset is our people, and as an afterthought, I'm going to tell you about one or two of them if I have time at the end. So I'm totally standing that on end, and like I said, if it works as planned, Jay has a clip that will show which will run for a couple of minutes and introduce you to some of the people that actually do the aeronautics research. So with my fingers crossed, we'll give this a try.
NASA is doing research in both the aircraft or vehicle side of the aviation system as well as the operations side, or how the aircraft operates in the National Airspace System. On the vehicle side, we are doing research and development into airframe technologies, lighter weight, composite, non-metallic material structures to make the airplanes lighter and therefore burn less fuel. We've been operating on what we refer to as a tube and wing type concept for many years now, and we're looking into novel architectures. We have done preliminary research and flight testing on a hybrid wing body type aircraft, which basically looks like a flying wing. We're also doing research in how the aircraft operate in the National Airspace System.
This is the James H. Starnes Structures and Materials Laboratory. We've tested aircraft components in this building since the 1940s. We test trying to determine how a structure will perform in flight. What we try to do with the test specimen is we push it or pull it or twist it until we cause it to break. We want to get the best load carrying capability, the strongest structure for the least amount of weight.
The X-48B is the epitome of all the work that has been done in looking into the blended wing body concept. The blended wing body concept is a unique shape. I look at it as the middle ground between a conventional tube and wing aircraft and a pure flying wing.
Since 2000, Karen Taminger has been nurturing an idea that's now becoming a reality, destined for space. Taminger, who works at Langley Research Center, and her team are developing a technology to quickly build parts anywhere, even in space, without gravity.
I lead a team of 7 of us that look at data from commercial aviation and develop tools and technologies for data mining on that data so that analysts can use that to find operationally significant anomalies.
Right now we have several aeronautics programs that are working on reducing noise as part of our whole green aviation initiative. Some of them are worried about propulsion noise, the noise that the fan makes, and some of them are worried about the airframe noise, the noise that the landing gear and flaps and slats and everything else makes that make the aircraft so noisy on approach. There's a lot of fundamental science that still needs to be done to understand that, to understand ways to reduce that. So things like the serrated edges, these chevrons on these nozzles here, when applied to helicopter blades, can potentially also be a reduction for helicopter blade noise. And that is at a very fundamental level, understanding how that all works is what NASA is all about.
Okay, so I showed that for a couple of reasons. One, because the people actually doing the research in aeronautics are far more eloquent than I am in describing what they do. So hopefully the remainder of the time up here it won't be a disappointment for you. But I also, borrowing from our field, aviation, when you get on an airplane now, the safety video, most airlines know if they show a video, the passengers will actually watch. If a flight attendant's actually reading the script, most people will continue to do their crossword puzzles, read their books, and turn off their cell phones. So hopefully that worked here, and you got a brief snippet of the type of work that we're doing in aeronautics research. So the next thing I wanted to talk about past the people who actually do the work is where we do our work. And I assume most of you have some association, either are NASA employees or have some association with NASA. And so our work is done at the 4 research centers. So Jay, if you can go to the next slide. Ames Research Center and Dryden Research Center in California, Glenn Research Center in Cleveland, and Langley Research Center in Hampton, Virginia. And all of the research centers historically have specialties. Langley was the original NACA center and really has a lot of expertise in aerodynamics and airframe type of work, or aerosciences. Glenn started as Lewis Research Center as a propulsion center. Ames actually has a varied history, but most recently has gotten heavily into air traffic management type of research activities. And Dryden, of course, is co-located with Edwards Air Force Base and is our flight research center. The nice thing is, at one time, I think these were known as Aeronautics centers or CODAR centers, if you remember that version of NASA. But anymore, the portfolios are really quite diverse in terms of the type of work performed at the research center. So it's a good mix of space or human spaceflight related activities, science activities, and aeronautics activities. And quite honestly, to me, that's an advantage, because many times people doing aeronautics research also are either doing work or research for one of the other mission directorates or programs, which is non-aero. And what I've observed over time is some of the practices that occur in the development or flight programs, which aero researchers may get involved with, in terms of just the rigor of program or project management, or just the diversity of the type of things that they're exposed to, the difference, the way you have to respond with research in areas like structures and materials or instrumentation and controls to a space environment as opposed to an aeronautics environment, has really paid benefits for aeronautics research. And so I think the diverse portfolio is actually a good thing. Now, if that sounded like gratuitous sucking up to an astronautical crowd, it wasn't in a way, but I hope it was. It really was sincere. I think it's been good for the agency to have employees at the research centers really see the whole breadth of what this agency is all about. So that's where we do the work. So the question is, what do we do? Well, we do have, I think Dr. Holdren or Charlie Bolden mentioned on the first session the space policy, which came out of the Office of Science and Technology Policy. We also have an aeronautics research and development policy and plan, and that has some principles associated with it which guide the investment of the federal government in aeronautics research. And our portfolio in aeronautics research and our programs align very well with the principles in that policy. And so in that, if you were to read that policy, you would see things like we need to make advances in mobility and efficiency of the air traffic management system. We need to make advances in terms of energy usage and efficiency of vehicles themselves. We need to make advances in safety, and we need to make advances in both the security of the aviation system and then in national security as well. So our program is structured that way, where we have three fundamental research type of activities, and here they're listed as vehicle safety and air traffic management. And that's really what I think we typically know as maybe basic or applied research. Not so much basic, that's more the purview of academia or the National Science Foundation, but basically applied research, low technology readiness level. And maybe a missing part of our portfolio for a couple of years was more the higher TRL, or what we're calling integrated systems research. And so within the last couple of years, we've added a component to our program which is really sort of our centerpiece in terms of what we hope to accomplish in terms of technology transfer, and that's our integrated systems research. And then we do sustain some large ground test facilities in the flight research assets and the infrastructure that supports flight research, and we call that our aeronautics test program. And so the facilities are really pretty much underpin our the required capabilities that we need in terms of either ground testing, modeling and simulation, or flight research itself, and an important aspect, I think, for NASA to sustain those not only for our own research purposes, but for the nation's needs as well. So that's just a real quick smattering of the programs. The highlights highlighted on the next chart are maybe truly the things that Alan said, things that you don't know, and we always look for one of the things that we measure ourselves against as an R&D program is our relevance. Are we really making a difference to the community? And one way I think to accurately measure or have a sense of whether you're making a contribution or not is when you're recognized not by yourself but by others in the field. And so recently we've had some pretty significant external recognition of some research activities that we've been doing. The first is a helicopter a rotor blade test performed in the 40 by 80 wind tunnel out at Ames, where we took very large blades that would be applicable for both helicopters and also Stovall type of aircraft, and did a number of measurements which have not been done before on blades of the size that we actually used in this test experiment. And that particular effort was recently awarded the American Helicopter Society's Grover Bell Award, and that particular award is for encouraging research and experimentation in helicopter development. In fact, the AHS annual meeting is, I think, in Norfolk in a couple of weeks, and that team will be recognized at that meeting. Also, within the last couple of weeks, Aviation Week held their Laureate Awards ceremony, and we had a really interesting collaborative effort with the AFRL, or the Air Force Research Laboratory in Dayton, where we were testing and developing an automatic collision avoidance system or technology for fighter aircraft, which we hope to continue to develop and commercialize for use in fields like general aviation, where putting electronics or instrumentation on aircraft can oftentimes be cost prohibitive. But this is a really promising technology, and that was awarded one of Aviweek's Laureate Awards. And then we hit a streak where we were awarded a couple of Collier trophies in a row, although I think this year a helicopter-related engine development program that we didn't have anything to do with is one. But the commercial aviation safety team was formed probably about a decade ago or maybe more, and in that time period the fatal accident rate has plummeted, and it really is a great example of a cooperative effort between the industry and the government in terms of assessing how we do aviation safety and how we make advances, and a tremendous effort. And that was recognized in 2008 with the 2008 Collier Trophy. And then the year before that, the system that will replace the ground-based radar system for tracking air flight, known as ADSB, was awarded the 2007 Collier Trophy. And there's really a great connection between space and aero, because the backbone of ADSB is obviously the global positioning system, so that we know where aircraft are in space and time at any given instance. So that's just a smattering of highlights. And so the real question is, okay, that's all good to know. You have a policy, you've structured your program to align with that policy, you've got really enthusiastic and eloquent people doing your research program, but why is the federal government doing aviation research? And we are asked that question, if not continuously, we're asked frequently, why after 100+ years is the government still doing aeronautics or aviation research? But there are any number of advances yet to be made, and so we start with aviation's economic impact on the U.S. The number of jobs and both the direct and indirect benefit to the economy is significant, and the number of flights is very large, and the number of people that fly every day is significant, and the positive trade surplus for this particular country makes a huge difference. And in a second I'll sort of bring that point home about like what it costs to operate the nation's air transportation system. You see the economic benefit here, but there is a significant cost, and a lot of what a lot of what we do in terms of our fundamental research, which would advance energy consumption and make both vehicles and the whole air transportation system more efficient, really is with an eye toward driving down or holding down the cost of operation of the entire system. So I think next I have a video, and while that's running, for those of you who were here last year, Jaewon Shin participated. He's the AA of Aeronautics, participated in a similar panel. This is called the Fencin Software, and quite honestly, I've forgotten exactly what FACET stands for, but this shows a simulation, a 24-hour snapshot of the entire world and every flight, one day's sort of a day in the life of the world's air transportation system, and soon you'll start to see little blips of light, and each one of those blips of light represents an aircraft flight, and you can see as the country wakes up, the East Coast traffic really picks up, and then as time goes on, the West Coast wakes up as well. Now, obviously, we've increased dramatically the scale of any blip of light. If we did it to scale, you probably wouldn't see anything because it would be a micron or less size. But it does give you an idea of the congestion and the amount of air traffic in this country at any given time, and how much air traffic control is dealing with. In fact, if you read the Washington Post, the front page of Section B this morning, you read an article about the go-arounds or the aborted landings at National Airport, and if you read the whole article, you eventually got down to the controller's dilemma. Pushing 700 plus flights through National Airport every day is quite a challenge with one runway, and so basically what air traffic management or air traffic controllers have to do is just stack up flights one after another so that the timing is such that takeoffs and landings coincide, and after a while, especially during the times when everybody wants to fly, morning and evening, you've basically compressed everything down to almost that perfect timing, so that if a plane arrives just a few seconds earlier or later than it was planned, there you've upheaved the entire system. So it's now an entirely manual system. Our air traffic
space shuttle program. About that with a computer generated.
From that talk, and it was very interesting. In 2003, if you can flash back to 2003, we were kind of in the middle of the Columbia recovery. We weren't sure exactly where we were going with exploration. We couldn't talk about destinations. We didn't really have a plan for exploration, and it was eerily familiar to me to where we are now in 2011. And I used this talk to talk to the folks in Wright Pat and the Dayton area and the aeronautics side is, when the Wright brothers came together, they didn't have a mission statement or a vision statement. They didn't have PERT charts and Gantt charts, earned value management systems, 7120, could go on and on about all the things that the Wright brothers didn't have. But they had a deep-seated passion and love for what they were doing. And they had a tremendous inquisitiveness about how to move forward and how to do testing where it didn't exist. You know, they used a bicycle wheel as a quasi-wind tunnel to look at airfoil shapes. They didn't take the airfoil shaped books that gave you lift drag curves. They went off and did their own work, and they pushed that on their own. And they did that pretty much as individuals. So I think, you know, my point of the talk back then and my point of the talk today is we need to think about it as an individual with the passion that we have and what we can do to push our industry and push where we're going in our own direction. So they may be small things and they may not seem big, but could the Wright brothers ever imagine what is seen in this image? Could they have ever imagined, you know, an 800,000-pound spacecraft flying overhead with a Russian vehicle attached to it? Not only a Russian vehicle, but here's these structures out on the side that look like. Never imagined. Human drive. So the individual, each one of you in this room counts an awful lot. Okay, this is another kind of thing that is pretty timely. You know, the Japanese earthquake and tsunami occurred, we lost our flight controllers in Japan for a period of time while they had to determine if their control center was safe to operate and go back and rehabilitate. They were able to do that. Their module, their cargo transfer vehicle, the HTV, was on orbit, and at the time, so they essentially powered things down, handed control over to Houston for a period of time, and then they came back and operated. Last night, about 10 o'clock, the Japanese HTV cargo vehicle re-entered the atmosphere, and before it re-entered, so then we sent up to the crew in typical fashion a one-page procedure on how to fold I personally tried and I failed, so that's probably why I wasn't on orbit. But you can see over on the right, the crew is actually able to construct the frames, and then you can hardly see it down in the picture in the lower left, but that's an actual view into the hatch of the HTV of about 15 or so cranes actually floating in the HTV, and those re-entered. Last night at 10:30, I got a note from my Japanese colleagues, and they said basically the cranes have re-entered into the Pacific Ocean. Thank you very much. So what a spirit of cooperation there now exists in space, even beyond the actual technical accomplishments, but now the actual personal ties between the controllers in Japan and the people here, as well as the crew on board Space Station. There's another whole new dimension in international relations that are going on. Next thing is, we'll talk a little bit about is how not to use social media. We decided to sponsor this contest called Name the Node Contest. This was the name Node 3. So we crafted this thing with all the right filters to do things right, put all the stuff in place. We put an unbelievable legal disclosure on the bottom that these are just suggestions of names. NASA reserves the right to pick whatever name they want, et cetera, et cetera, et cetera. So we were covered from all the legalistic standpoints. And then this contest kind of took off on its own and went viral, and we were getting in serious trouble. And Xena, the Warrior Princess, was number one for a while. I don't know much about it. My yearbook zoomed into first, and that's another thing that I don't know much about. But I understand high school kids now no longer sign yearbooks. That's old school. You actually email things back and forth, so you have an electronic record of all your friends sending you wishes instead of having them in this archaic piece of paper with ink and writing on there. You now have it electronically, so you can digitally carry it around next to your life for the rest of your life. that was for a while, and then the Colbert crowd took over, Colbert Nation took over, and they actually won. So in some ways, it was good that they won, because I don't know how I would have dealt with Xena or my hero. But we ended up with this, and then that was fine. Except I didn't really want to name the node Colbert, and that was all fine until I got a letter from one of our House members who explained to us that the popular vote there, what were we going to do? So then in typical fashion, we came up with this clever thing from my friends in Houston. We were getting ready to go launch the treadmill. And it's not really the treadmill, it's a combined operational load-bearing external resistance. And then we had to talk to Mr. Colbert to see if we'd agree to all this, and we ended up naming the node Tranquility, and the treadmill became the Colbert. We call it T2 sometimes as well. But the point of all that is, it sure didn't go the way we anticipated. I think in the end it came out okay, but boy, it took a lot of creativity and agility through this process. So this is another thing imagination is. So more than you can imagine, I had no idea this would come out the way it did, but it did. And I think it's still a good thing that we need to think about is how we reach that younger generation and use tools that they can see. Next. This is another thing that's pretty interesting. This is on board Space Station. This is a hyperspectral imager for coastal oceans. You can hit the next one. It'll show you what we're looking at. We're looking at Baghdad, Iraq, and then the Chesapeake down below. What's interesting about this is this was flown up on the Japanese HTV, the first rocket. It was a kind of a research kind of payload. It sits out on the Japanese segment. It sits out on their exposed facility. And it's a pretty effective hyperspectral imagery. And what's interesting about it, and the reason I put it up here is, it's the way I think station fits best. It's not a good operational platform, because whenever the crew runs on the treadmill and does their exercise, some vibration comes back into the truss. When the solar rays move, it also vibrates a little bit and causes some blur of the images. When the shuttle comes up the dock, Progress comes up the dock, Soyuz comes up the dock, they lose imaging depending on where the vehicles have come up. But it's a great tool to just calibrate the instrument and see what the instrument is good for. They did some things here. They used a computer that is not a space-rated computer that controls this. Some of the control systems are not exactly space-rated, and they've been getting data for over a year now, probably almost a year and a half. And so it works out really good. They can actually experiment and learn some new things, and so it shows that the station works well as a test bed, but maybe not as good as an operational instrument. But I think it's good to know, and maybe I don't know if you do, but stations actually being used for some Earth observation activities, and this has been a pretty successful thing for us, and we'll try to do some more of these. Next. This is another thing. This is the spheres. These are these little plastic spheres that maneuver around inside a space station. They have a control system. They use carbon dioxide as the propellant to actually maneuver them. They can fly in formation in space. They can keep track of each other. And what we've done with this is we're letting students, high school students, actually program these with tasks. So you can think of it like the robotics first competition, where the robots are on the ground, but now these robots are in space. They actually build rendezvous proximity operations software to load into these devices. And we've got some challenges where we have the MIT students build one of these satellites as, say, a blocker, and then the other two are supposed to fly past this other one. So it's the high school students against the MIT students, and who can actually build the best code and uplink from a rendezvous prox op standpoint. So it's been intriguing to see the interaction. It's really been good for both the university and for the students. It allows them to get together. They'll go to the flat floor at MIT before they actually log their software into the Spheres Onboard Space Station. So the university gets a chance to see students that have high promise. The students get a chance to see what the university is like, and do they want to enter the field of engineering. So it's turning out to be a very, very positive thing. And so we're going to continue to do some more of these things, some more challenges along those lines. These are very neat spacecraft. They can actually transfer power back and forth. You can add extra boxes on the outside to look at things like fluid slosh and spacecraft and other things. So there's lots of areas we're going to keep pushing this, and we're doing this along with DARPA. So DARPA is contributing with us in this activity. So next. This is the next thing that's getting ready to go fly. This is the alpha magnetic spectrometer. I always, probably you guys know more about this than I do. I like this because there were actually cosmic rays in the space station processing facility in Florida, and that's what these charts are. So the first time I got to stand next to the AMS and this thing starts beeping, I go, what's going on? And I go, those are galactic neurons or neutrons coming through the atmosphere and actually impacting the detector. That gave me pause. I didn't realize what actually is happening at the cave, and they're probably going to actually publish a paper out of this. This is the first time they've ever actually looked at these particles, on the ground in this way. This would be typically done in an accelerator, like the CERN facility, where they look at those particles. But you can actually see as they impact the roof of the SSPF, and actually as they splinter into other subparticles. So this is going to be really interesting data. So if AMS does this well on the ground, it'll be very interesting to see how well it does on orbit, and it's scheduled for the next shuttle flight. So next. So since this is the week of the Goddard activities, and you guys are mostly engineers, I thought I'd give you some numbers, so when you're at cocktail parties, you can talk to your friends about these numbers. So now it's up to you to tell me what these numbers mean. So what is 961? Does anybody know? Scott Navigator? No, not number 5. Next slide. All right, so we'll go to the next slide. Now we'll give you these. So now these things you need to memorize. So when you're eating hors d'oeuvres and you've got a little wine glass at the Goddard dinner, right? You should be free to talk about these with your friends and impress them with your knowledge of space. So the first one is pretty amazing. We've had, for the International Space Station, we've had 961 hours of spacewalks. So roughly, if you divide that by 24, you know, that's like 40 days of spacewalks to assemble the space station. That's pretty amazing if you think about it. 110
from all vehicles have been to the space station so far. Another pretty amazing number. 32,033 feet of cubic feet of pressurized volume. That's about the size of the internal volume of a 5-bedroom house, roughly. Pretty amazing. 827,000 pounds on orbit. And this is another one especially for the dinner crowd. 23,000 meals have been eaten on the International Space Station, which is pretty amazing. That's the human piece of us. 1 million lines, 1,800,000 lines of code is pretty neat. 90 kilowatts of power, and you can relate that to things here. And then there's probably, we estimate, around 100,000 people with the civil servants, contractors, international folks that are working on the space station. So these are pretty interesting, just kind of gee whiz numbers. But I thought, in the spirit of imagine and things you may not know, I thought I'd give you some numbers you could talk about. Next. Another thing that's kind of interesting is you think about the 16 countries or the 4 partners that run Space Station. We really have about 59 countries that have participated in ISS utilization through 2010. So that's pretty phenomenal. So when you think international, it's much more than just the 4 partners and the ESA delegation. We break them out here a little bit, but you can look at this list and it is pretty diverse if you look at who's participating in the space station. Next. And this is a little bit on the research side. I like this chart, and you don't need to read all the details on the graphs, but what I like about it is it shows the major countries, the Canadians, the Europeans, the Japanese, NASA, and Roscosmos. And then the color bars, those show the types of research that they're doing. So they're things like technology is kind of the bottom line there, then physical sciences, then human research. Educational activities are in yellow. Earth and space science and biology and biotech is the top one. But what's intriguing to me is the beauty of Space Station is no country needs to follow the same model. So you can see how each country has kind of focused their area of research in a different area that they want to go pursue. So this is very intriguing to me because this shows the potential benefit of stations. So even though we're focused on one particular area, you see NASA does a lot of education. You can see JAXA doesn't do nearly as much education, but they're very big on the biology and biotechnology. So you can kind of see how each country has chosen their area of expertise to go participate in, and I think that's one of the real strengths of the stations. It allows the countries to choose the field of research where they want to go do their investigations. And through Expedition 24, we're on Expedition 27 now, there's been 1,000 investigations. 454 of those are considered completed. 700 of them have been partner investigations. The national lab investigations are things sponsored by the National Institute of Health, other government agencies that are participating. About 1,600 scientists, and then quite a few scientific publications, and we're still trying to get a better handle of displaying that. So I think it's important to note that Station isn't just a large engineering accomplishment, it has tremendous research potential. And next. And that's really all I wanted to talk to you about at this point, and I'll answer your questions at the end. But hopefully you learned something, or hopefully I armed you with a number that you can use at the Goddard dinner later in the week. Thanks.
Thanks, Bill. Well, that definitely checked off the box of things I didn't know about Space Station. So for all those whiners that talk about Space Station just goes around and around to nowhere, I think everybody should see this presentation of all the things Space Station is doing and all the things it will be doing over the next 10 years. Also, while I said I wouldn't say anything career limiting, I turned off the censor for a minute. I continue to use every venue I can that I believe the partnership, not the not the facility itself, but the partnership of the International Space Station. And you see now not just the 16 partners that are involved, but the 59 countries that are involved in experiments. I believe the partnership deserves to win the Nobel Peace Prize. So if you know anybody who's on that committee, please tell them when I leave NASA years from now, I'm going to make it my personal quest to make sure that happens. So let's move a little further away from orbit, low Earth orbit, and start talking about exploration. And for that, we have Dr. Laurie Leshin. Those of you from Goddard are certainly familiar with Laurie from her days as the Deputy Center Director for Science and Technology. She's been down with us at headquarters now as the Deputy Associate Administrator for Exploration Systems Mission Directorate. What you might know about her is that her areas of expertise are cosmochemistry and geochemistry, and she especially likes to work on deciphering the record of water on objects in the solar system. So that whole follow the water thing must be fascinating to her. Another point you may not know about her is that the International Astronautical Union has recognized her contributions to planetary science and has named an asteroid after her, asteroid number 4922 Leshin. And this gave me a great idea, so that for $50, I will name a galaxy after any of you. So, Laurie?
Okay, thank you very much. Yes, yes, obviously I'm trying to make sure that when we go to an asteroid, it's mine, but no, it's not a near-Earth asteroid. It's not going to come anywhere near us, so I don't want to be responsible for that. Well, thanks, Alan, and it's wonderful to be here with so many of my former Goddard colleagues. I miss you all a lot, and you probably can't even imagine how much. Maybe you can. I love the theme of this conference. The idea of imagination, as Bill so eloquently spoke about, really expanding our minds as we move forward in our commitment to the future of human spaceflight. But in fact, some things have already happened here today that I would have had a hard time imagining. The most important of which is, here we are at an astronautical conference, and there was a line in the ladies' room. Who would have imagined that? Right on. I like that one. That one wasn't so hard to imagine. So, I do think this is a moment for imagination and creativity as we think about moving ahead in our exploration program. Unlike Bill, I'm going to talk a little bit more focused on what is actually the content of our program moving forward. Because it's been, you might say, a dynamic time in the history of exploration, I think it's really important that we focus on where is it that we're putting our energies going forward, and to give you guys an update on what it is we're doing within the exploration program. So I am going to kind of give you a standard pitch about the components of exploration, but I'll try and highlight some stuff that you may not be aware of as we go. So it starts, as both Charlie and Dr. Holdren emphasized this morning, with the Authorization Act of 2010, which was, of course, a bipartisan, as NASA support almost always is bipartisan. We're very fortunate as an agency in that way. Support for our plan moving forward. And that was passed last year. And just to kind of quickly summarize the key components of what that law authorizes NASA to do going forward. One is the extension of the ISS to at least 2020. Again, extraordinarily exciting that we know we're going to have this, our toehold in space, if you will, as we move out beyond low Earth orbit. Strong support for the commercial space transportation industry to create both the cargo and crew transport to ISS. We'll talk more about some of these things as we go through the presentation. Then development of the systems that are going to take us beyond low Earth orbit. And there are two key systems that we'll talk about. Initially, one is the big rocket, the Space Launch System, SLS. Again, you heard that mentioned already this morning. And the other is the crew capsule, the crew vehicle, what we call lovingly the MPCV, the multi-purpose crew vehicle, which means it can go to multiple destinations. It's not just for one place. So the MPCV, you'll hear about that. We'll talk, and I'm not going to give you a whole lot of the why and the philosophy behind all this. That's my talk actually in the afternoon session. So if you want to get into a little bit less nuts and bolts and more of the sort of broader picture, we'll talk about that this afternoon on the Future Human Spaceflight session. But it is a flexible approach to future space exploration, what I'll call a capability-driven approach. That is, we're not talking about single destinations by certain dates. We're talking about opening the solar system to human exploration for good. And that is driven by the capabilities we develop over time. And this Authorization Act endorsed that approach. And things like including the moon, near-Earth asteroids, Lagrange points, Mars and its environs, all of those destinations should be opened up to us if we do this right and do it well. And finally, the support for that in space technology program. So investing in the other capabilities we need to get beyond low Earth orbit and driving innovation nationally as well. So those are the main components of that law, which are broader than ESMD, than exploration, but a lot of them are focused on the work that we're doing. So as we then focus in on exploration's 12 budget request, I want to just talk to you about how I kind of think about these pieces going forward. First of all, it's a nearly $4 billion request for exploration, which is a bit over the FY11 authorized level, so that's a good thing. In these tight fiscal times, the commitment to exploration remains strong. You saw that it was strong in the Authorization Act. Here's evidence that it's strong from the President as well. So that's good. Our commitment, and again, this conference is about imagining, and we can all imagine a future beyond low Earth orbit. I'm here to tell you that our organization at headquarters, and I hope all of you will join us in a strong commitment to that exploration beyond low Earth orbit. That is what we're about as an organization. So, the FY12 budget request, the way I think about this, it kind of breaks down into three chunks for me. One is the low Earth orbit chunk, and that includes ISS, which is over in the, on the SOMD side of the house, but exploration comes to that table with the commercial space industry investments that will ultimately are leading now, soon to lead to the ability to resupply the station's cargo, and in the future will lead to our ability to purchase commercial services to transport crew back and forth to station. So making sure our investment in LEO is strong and sound is the first step in going beyond. And it's not just the commercial industry investment that's key to that from our perspective. It's also using ISS, using that amazing capacity that we have in space as a test bed, as a laboratory, to really, in many ways, launch, if not physically launch, but launch many of the ideas and concepts and validate those ideas and concepts in space. So we'll be leveraging ISS a lot. So that's the one piece. The first piece is the LEO piece. The next piece is, what are those key developments of key space systems we need to get out beyond LEO? And that's where the big rocket, the SLS, and the multi-purpose crew vehicle come into play. So those are funded in this budget in FY12. And we'll talk more about all of these as we go through the presentation. And then there's a third piece. So the SLS and MPCV are required. They're necessary. We'll talk more about them. But there are other things that are necessary too. Those are necessary, but they're absolutely not sufficient. We need other capabilities. We need to upgrade our capabilities in order to be able to go beyond low Earth orbit. There are many things we don't yet understand how to do. We need some fundamental research as we go forward into human systems that are going to help humans not only survive but thrive on long space journeys beyond low Earth orbit. We need to understand some things about our destinations as we go forward. So that's the third piece. It's the research and critical capabilities development that we need to get beyond. So that's kind of how I think about this budget as we go ahead. And the great news is those three areas very much sound like what was on the last slide, right, about the Authorization Act. This budget supports all components of that Authorization Act as we go forward. So I really do feel like we've started to congeal around what our plan is from here forward. Now, is it going as fast as all of us would like to be able to, say, okay, I know exactly what this rocket's going to look like, or I know exactly what's going to be funded where? Well, it never goes as fast as we'd like, but the point that we should take right now is this is the inflection point, I think, was the word that Dr. Holdren used. It is an important moment to stop and make sure that we are starting on the right track, starting on the right foot. If we need to, with all move ahead aggressively, but do so smartly. Now's the time that we are taking the time to do that. So to talk a little bit more about these components, the next slide talks about the rocket, the SLS, and the MPCV, which is in that expanded view on the bottom there. That's the little capsule in the middle. So this budget funds a total of almost $3 billion for the development of these two systems. So 1.8 for the Space Launch System. And again, you can see our reference design vehicle there is based on existing shuttle and Ares-derived hardware, but we are taking the time to study options and make sure that we're approaching this in the most prudent way possible. So this will be the vehicle that lifts our cargo and our crew out beyond low Earth orbit for these deep space missions. And it's going to initially have a capacity between 70 and 100 metric tons. And again, the idea of making it evolvable that Charlie talked about this morning, up to, say, at least around the 130 metric tons range, which is the kind of capability we need to get to Mars. The multi-purpose crew vehicle, it's again, that's the vehicle the astronauts ride in and sustains the crew while in space and brings them home. And then there are some, ground operations, ground processing, mission operations, things that go with that as well. So again, almost $3 billion a year to be developing these new systems. Next slide talks a little bit about our status on these. This is obviously of interest to a lot of folks. We have planning teams in place, and when I say planning teams, it's not 3 guys in a room. We've got 200 people at Marshall working on SLS right now, so we are aggressively moving out on the launch vehicle. And the crew vehicle, we've got in place the Orion team that is working on transitioning to the multi-purpose crew vehicle. So the SLS team is developing those program requirements. Obviously, the heavy lift launch vehicle is not as mature as where Orion has been in its plan, so they're developing their requirements and working towards system requirements review, maybe in the FY12 timeframe. They're looking at different vehicle concepts, and again, having a sense of what the budget is going to be is helping drive that conversation. We need to make sure that what we're doing is affordable. That's the key to sustainability here, right, as was discussed earlier this morning. So we're looking at how we can smartly implement these new vehicles in order to stay within our budgets and deliver on timescales that will really make a difference for moving beyond LEO. So we're using internal study teams. We've got actually 4 teams working down at Marshall, and then we've also engaged industry. We've got 14 industry partners through a broad agency announcement that we did a few months ago, and those teams are interacting, and the industry teams are feeding ideas into the NASA teams, and the NASA teams are looking at different very different architectures for the launch vehicles and trying to understand how we infuse affordability and innovation in all of those different vehicles. So it's a very exciting time. We're starting to hear some outbriefs from them and getting some sense of the results there. And there's a lot of wonderful ideas and wonderful energy. Give a ton of credit to the folks down at Marshall doing a great job. And you may hear more about that from Todd this afternoon. I don't know if Todd's here yet. Todd May, who's on the panel with me. Wait, go back, not quite done yet, sorry. They're looking at things like existing contracts, things we have in place through the Ares program, through the shuttle program that we might be able to leverage and use on that as we go forward. We're looking at different procurement options there and are not yet to conclusion about the best and most effective approach. We're looking at early test flights. How can we make sure that we're flying things and learning things as soon as is prudent? And then for the MPCV team, again, we've got the current Orion team with Mark Geyer and his team in place at Johnson Space Center. And we're looking at the MPCV requirements and comparing those to the Orion requirements. Not surprisingly, they're very similar. So we're looking at sort of documenting that as we go forward there. And in the meantime, these guys are building hardware. There's a picture here, and there's a better one on the next slide in a second, of the Orion ground test article, which shipped from Michoud a couple months ago, is now in Denver being tested. So we've got real hardware that's being developed that is going to help us advance the ball on this crew vehicle. And again, we're looking at early test flights and the contents of those flights. So I would say we're moving out aggressively but deliberatively at this point. It's a very exciting time in the formulation of these programs. Next. Just to again show you that basically we're standing on the shoulders of giants here. We're standing on the shoulders of the previous work that's been done in exploration and on the current work that's ongoing in exploration. Things like this ground test article in the upper left, that's the innards of an Orion capsule test article. Beside that is our 5-segment rocket motor firing, the DM2 firing from a few months ago. Out in Utah, great work by ATK. We're looking at autonomous rendezvous and docking. That's what AR&D is down there in the lower left. And I think it's the next shuttle flight, right? We're doing a test of some systems on autonomous rendezvous and docking. So again, that's going to be very useful as we look at these architectures for future human missions. We're going to need to be assembling some things in space, and so rendezvous and docking is a very important component of that. And of course, we had the very successful Pad Abort 1 test. So that's the launch abort system. It's over horizontal here in the lower right, which yanks the crew off the top of the rocket in case of a bad day. It gives you quite a ride, but it beats the alternative. So we've been continuing work on understanding the best ways to keep our crews safe. And it turns out things like abort scenarios are the things that you really have to think through as you're designing these rockets from the ground up. And they often tend to really drive the requirements. It's easy to think about, not easy. It's relatively easy to think about the nominal mission. It's when you get into these contingency scenarios that you really have to think hard about the most effective and safest vehicles to fly on. Okay, so next. So that's the first chunk. Remember, 3 chunks, actually, so I reordered them for you, but that's the Beyond LEO Systems chunk. Here's back in the LEO System chunk. So imagine commercial spaceflight. To me, this is extraordinarily exciting. It's a different way of doing business for NASA, and it's scary to some folks. We heard about that this morning. But this is a way of transitioning the things that, as of next week, we've been doing for 50 years, which is sending humans up to low Earth orbit, to the commercial sector to provide us as a service, and to decrease our reliance on our foreign partners for station crew rotation, which we're already reliant on them for that. So the goal of this commercial spaceflight investment, which is on the order of $850 million in FY12 in the President's budget request, is to facilitate safe, reliable, and affordable, cost-effective transport to and from LEO, and including the ISS. And the idea is we make investments in companies to help create this capability, and later we can turn around and buy a service from them. The great thing about this approach to it is they put skin in the game. They make their own investments. It's not just a government system. We encourage competition by having multiple partners. There's a lot going on in the planning of how we're going to do this program that's going to make it very exciting. And to me, the most exciting thing is the real hope and possibility that it does open up space travel to so many more people. The idea is, if we want NASA to be the organization with our international partners that's going beyond low Earth orbit, we kind of want everybody else to help fill in that low Earth orbit and help get all of us the potential to have access to space. So I see this as a hugely exciting thing. Let's go to the next. I just want to highlight and give some kudos to our current partners. Of course, about SpaceX and their extraordinarily successful test flight through our commercial cargo resupply program last year, and Orbital doing amazing things, getting ready for their first test flights later this year. But in addition, we've started very small investments in some companies interested in the commercial crew area. Just some initial tens of millions of dollars, and look at all the hardware we're getting for it. So I call this more hardware than you'd imagine we should get for such a small investment from our 5 different partners here. Many of you are in the audience today, and I congratulate you. Amazing things from composite crew capsules and Boeing capsule up in the upper left, and some new motors and life support systems from Paragon, and ULA's working on some new launch vehicle systems, all in support of thinking about using these kind of capabilities for commercial crew. I'm not going to say a lot more about that because we actually have another competition out on the street right now that's being decided upon. So, but very exciting possibility. We're seeing a lot of energy out in the commercial sector to get involved in commercial crew transportation. Next. And then here's the third piece. It's exploration, research, and development, which includes for us our human research program, which is at about $160 million in 12, and something we're calling the Advanced Exploration Systems Program, which is a relatively small $124 million in FY12. It is we used to have something called the Exploration Technology Program, and you'll hear more from Bobby Braun probably about that this afternoon, that a lot of our sort of true technology development stuff has been moved and consolidated with the Office of the Chief Technologist to really take advantage of some synergies there. We have kept in exploration some of the key developments of key systems and capabilities, more system level development for things that are really strongly coupled to our vehicles, things like life support systems and extravehicular activity, and the next vehicles beyond the SLS and MPCV, the space exploration vehicle that would either drive around the lunar surface or help us interact with an asteroid. We need places where we can prototype those vehicles and learn and test the heck out of some of these advanced capability area we need. So these are places, these are programs that are designed to help us keep our crews safe and always keep our eye on what comes next, not just focus in the here and now on the launch vehicle and the crew vehicle and commercial crew, which are really critically important, but there's other stuff that's required too, and this is a small but important investment in that. This program will also include support for some missions of opportunity on robotic missions. We're working closely with the Science Mission Directorate to look at opportunities to fly. We'll also be talking with our international partners about opportunities to fly. We've been thinking about what are those measurements you need in an asteroid in order to feel comfortable sending humans there. So we'll be looking to try and obtain some of those measurements by partnering. Next. So this is just the summary. Again, we in ESMD and with our partners at the centers and our partners in the commercial industry and our international partners are at an exciting moment where we really are daring to imagine sending humans into the solar system. And again, we're not just imagining it. We in ESMD, you can imagine it's been a challenging year. And so we've actually been spending some time as a team talking through and reaffirming the fact that challenging, we are absolutely committed to this goal, to sending humans into the solar system. And we're going to do what it takes to make that happen. And we're going to need your cooperation to do that, because there's never enough money to do it the way that we would like, but we're going to figure out and take those affordability measures and figure out how we do our NASA process to make these missions successful. So this budget request supports all key aspects of this plan going forward. That's great news. Everything that we need to be investing in is included in this budget, and we're gonna manage that portfolio smartly as we go forward. And, we take the challenge. Again, I've already mentioned that we take the challenge to execute these programs within the available budgets. And we're going to look forward to working with all of you to make that happen as we go beyond LEO. Thanks.
Thank you, Laurie.